All right, welcome back. Today we're going to do something pretty fun, so stick with me because today we're talking about binomial coefficients, right? And with binomial coefficients, we have this big question that we want to answer. Now, what is that big question? Well, the big question is how many subsets, here, let's write this, how many subsets of size k, how many subsets of size k does an n element set have? Now, that might not sound too interesting because, in real life, you're probably thinking, why would I ever care how many k-size subsets the n element set has, right? But this actually has so many applications to an infinite amount of counting problems. It's actually really cool and a lot of fun, and we're going to see that in the next video when we do some of those practice problems. But now, let's just actually talk about the definition, right? So we're going to say, let nk be natural numbers, right? So let nk be natural numbers. Then the symbol, the symbol, if I could write the word symbol, this is n choose k. That's how that reads. N choose k denotes exactly what we asked. It denotes the number of k element subsets of an n element set. Now, there is a formula for this. There's an equation, and we're going to get to that a little bit later. First, I would like to just do some examples, right? Let's do some case analysis, right? Let's think about this real quick, right? Let's think about 5 choose 0, right? So what that means is the number of subsets of size 0 of a 5-element set. Now, think about that for a second. How many 0-element subsets does a 5-element set have? Just one, right? That's just going to be the empty set. So this is equal to 1. Okay, cool. Now let's think about 5 choose 1. How about that? 5 choose 1. So we want 1-element subsets of a 5-element set. What is that going to be? Well, that's just going to be the singleton sets, right? That's going to be the set containing 1, 2, 3, 4, and 5, right? Okay, cool. So this is equal to 5. All right. Now, what about 5 choose 2? So this is how many 2-element subsets of a 5-element set exist. Now, this is going to be a little bit to write out. So let's just talk while we do this. So it's going to contain the elements 1, 2, 1, 3. Sorry that the squiggly brackets aren't that neat. 1, 4, and 1, 5, right? Now we have to do 2, 3. We're not going to do 2, 1 because we already did 1, 2. 2, 4, and 2, 5. All right, we're almost there. Now we have 3, 4, and 3, 5. And then lastly, we have 4, 5. So how many are there? There's 4 plus 3 plus 2 plus 1. That's equal to 10. So there were 10 2-element subsets of a 5-element set. Huh. All right. Well, let's think about 5 choose 3 for a second, right? 5 choose 3. What is that going to be? Huh. Okay, well, let's talk about something called the complement. I don't actually think we've spoken about the complement of a set on this channel, so we're going to do this really quick. So basically, if we have some space, call it X, right? Where X is a set. In this case, X will be the space 1, 2, 3, 4, 5, right? And then we have some set A, right? Let's say, for example, A is equal to the set 1, 2. Then the complement, which we'll call A bar, so you might see people write it like AC. Actually, we'll do that. We'll say AC is equal to X minus A. So it's the complement of A is all the elements in our space that are not contained in A. So in this case, the complement of A is going to be equal to 3, 4, 5, right? Because that's everything in X that's not in A. And maybe we've talked about complement on this channel before. I actually don't remember, but there's a little refresher, right? So now that we have that in mind, let's think about the 3-element subsets of a 5-element space, right? Well, we already did the 2-element subsets, so for every 2-element subset we have, there's also 3-element subset, right? There's the complement, right? So it kind of makes intuitive sense that we'll have the same amount of 3-element subsets as we will 2-element subsets, and in fact, that is the case. Oh, hold on, let's go back to that purple color. It turns out that that's the case. If I'm not going to write them all out, but you should if you don't believe me. Write out all the 3-element subsets of our 5-element space, and you'll see that there's 10 of them, right? One for every 2-element subset. And now the same can be said for 5 choose 4, right? Think about it. For each of our 1-element subsets, there's a set that has 4 elements. There's a complement, right? So 5 choose 4 is also going to be equal to 5. And then 5 choose 5 will be the complement of 5 choose 0, right? There's only one subset that contains all 5 elements, and that's the set itself, right? So there's 1, right? So that's going to lead into this proposition that I have for you, right? Let nk be integers, right? Then n choose k is equal to n choose n minus k, right? That's what I'm proposing, right? And it kind of makes sense, right? It should make sense with that complement definition. All right, now let's take a look at Pascal's identity. So, Pascal's identity, we're going to let nk be integers. With 0, actually, these should be natural numbers. I'm sorry about that. Here, let's write these. Those should be natural numbers because we're not dealing with negative size subsets or anything. So these are natural numbers, and in this case, specifically, k has to be greater than 0 and less than n. Then Pascal's identity says that n choose k is equal to n minus 1 choose k minus 1 times n minus 1 choose k. Now, we still don't even know what n choose k is, right? I haven't even given you an equation for that, but we don't need one. We just need our definition and some intuition. Now, what I'm going to do is I'm going to write out a combinatorial proof. I'm going to propose a question and show that both sides of this equality answer the same question. I'm going to pause the recording. I'm going to write out the proof, and then we're going to go through it together because I think that this will be very beneficial. So let me do that for you real quick. But you should also try to do this on your own. Okay, here we go. So it's not too long, right? And we're going to read through this together. So here's my proof, right? And remember, this is what we're trying to prove, Pascal's identity. Let me put that on screen. We're going to let nk be natural numbers, with k strictly being between 0 and n. Then n choose k is equal to n minus 1 choose k minus 1 times n minus 1 choose k. We're doing a combinatorial proof to prove this. So, the question I'm asking is, how many k-sized subsets of an n-element set exist, right? Well, clearly, n choose k, just by definition, right? So there we go. That's the left side of our equation. Now, let's take one element from the set a equals 1, 2, ... n. So a is our n-sized set, right? So we'll take one element from the set A and call it special, right? Just an arbitrary element, and that's our special element. Then we could say that all k-sized subsets of A either contain or do not contain the special element, right? Those are the only two possibilities, so that should make sense, right? All k-sized subsets of A will either contain the special element or they won't. So, if a subset contains the special element, right? So our subsets are of size k, and we already contain the special element. We still have k minus 1 spots to fill in the subset, and we have n minus 1 elements to choose from, right? So we have k minus 1 spots to fill because our special element already takes up one of those spots. And we have n minus 1 elements to choose from because our special element comes from that set of size n. So, and we can't repeat an element, so we have n minus 1 elements to choose from. So hence, n minus 1 choose k minus 1, right? Those are all the subsets that contain the special element. If that doesn't make sense, just pause the video, take some time to process that, and convince yourself of it. Once you're convinced, let's move forward. Now, if a subset does not contain the special element, then we simply have n minus 1 choices to fill our case-sized subset, right? And we have n minus 1 choices because we have an n element set, but our subset will not contain the special element. So that means we only have n minus 1 choices to choose from, right? And those n minus 1 choices are going to go into a k-sized subset. So that's where we get n minus 1 choose k from. That counts the amount of subsets that will not contain the special element. Again, if you need time to process that and convince yourself, just pause the video, let it digest, right? Take some time with new proofs, digest the information. Okay, so now that you've digested that, we'll multiply these quantities, n minus 1 choose k minus 1, and n minus 1 choose k, and that will find the amount of k-sized subsets of A, right? That multiplying comes from just rules of counting, which we've gone over way in the past. So, n minus 1 choose k minus 1, the total amount of subsets that contain the special element, multiplied by n minus 1 choose k, the amount of subsets that don't contain the special element. And that gets us the amount of k-sized subsets of A. And remember, A is an n element set, right? So since both sides of the equality count the same thing, they must be equal. And that's the end of our proof. Now that's pretty cool, right? We just proved this entire thing about binomial coefficients, and we still don't even know the equation for a binomial coefficient. Like, given an arbitrary nk, we don't even know how to evaluate that, but we just used our intuition, a definition, and a combinatorial proof to prove that. So now, for your valiant efforts, I'll give you what a binomial coefficient equals, right? And that's how we'll end this video. So you ready for this? So n choose k, I'm going to write this all big. N choose k, and yeah, n choose k is going to be equal to n factorial divided by k factorial times n minus k factorial. That's our equality. And now what I would encourage you to do is test out those cases that we were doing earlier, right? 5 choose 0, right? We found that equals 1. 5 choose 1, that equals 5. 5 choose 2, that equals, what did we get? We got 10, and that's equal to 5 choose 3. 5 choose 1 was equal to 5 choose 4. And 5 choose 0 was equal to 5 choose 5. Sorry, don't write those as fractions. Don't make that mistake I did. These are not fractions. So use this formula and see if we get those same answers. And you will, because we counted them out. But yeah, that is our equality. That is our equation, our formula for binomial coefficients. N choose k is equal to n factorial over k factorial times n minus k factorial. And if you're wondering what we do when k is greater than n, if k is greater than n, then n choose k is equal to 0, right? You cannot get a 6-element subset from a 5-element set, right? You cannot, 5 choose 6, that doesn't make sense. It's 0. So we'll just define that as 0. K should be strictly less than or equal to, here, let's write this. There we go. K should be less than or equal to n and greater than or equal to 0, right? So there you go. There's our formula for it. And in the next video, you still might be wondering, okay, that's cool, Johnny. We did some cool math. We learned about this cool mathematical object. But how does this actually apply to real life, right? And that's what we all want to know when it comes to math. Why are we doing this? In the next video, we're going to do some really cool problems. We're going to show how we can have these interesting counting problems and we can solve them using binomial coefficients. It gets really cool, I promise you. So look out for that. But for now, if you made it to the end of this video, thank you for watching. I really appreciate it and I hope you learned something.